Good morning, my name is Dan Barber. Together with my teammates Ian Shea and Felipe Sanchez, we'll be introducing you to the Capstone project sponsored by Semiconductor, bench automation design for the estimation of transient thermal resistance. Currently shown on the screen is what is the current test performed at Semiconductor in order to measure the transient thermal resistance of a field effect transistor, also known as a FET. It consists of a device under test, as well as various bench equipments and a measurement circuit. The engineers currently use one of two measurement circuits depending on the type of FET that is being observed, and the engineer will currently adjust the bench equipment or currently adjust the bench equipment and read the oscilloscope by eye. We see that there's a lot of opportunity here in order to improve on time. So in order to get a better sense of the test, we went and observed the test being completed. As you can see, it's definitely an inelegant setup. We have parts being taped down. We have clips holding the resistors hanging off the tables. And when we observed the test, we saw wires come loose. We saw that you have to manually change out the resistor in order to run a different power level. And we felt that this could be optimized by including both measurement circuits and making it a way that you can just simply plug in and walk away. So what's shown on the screen right now is a current automation setup that's employed to measure a different parameter of a FET. It's just to give you an idea of how ours will look. It's going to look a lot cleaner. There's not going to be wires hanging everywhere. Our best anticipated outcome, like we had said before, we want to achieve automation. It currently takes 2 weeks for them to conduct a thermal resistance measurement. And we want to reduce that down to just a single day, where they can enter in the parameters on the computer, set up the board, walk away, and it will be completed by the time they finish the day, interact with other customers, work on other projects. The second part of our best anticipated outcome is verifying theoretical values that they're given by a separate entity that only looks at it from a theoretical viewpoint. They don't actually have any physical data. So our numbers need to be accurate enough that they'll either complement the numbers that they're getting, or there's reason to question them for being too conservative or being too liberal. The last aspect in order to achieve our best anticipated outcome is modularity. What we mean by this is we want to include both circuits on the board. We want to be able to just put a daughter card onto the motherboard and run it for that specific device. We don't want to be producing a new motherboard every single time we want to test a new FET.
So this is a general overview of our system. A computer will interface with various pieces of bench equipment connected to our PCB or printed circuit board. The computer, using software, will be able to store and collect data observed by the multimeter and the oscilloscope, as well as send commands to the power supplies, the thermal stream, which controls temperature, and our microcontroller. So the way we actually test for thermal resistance is we apply a large amount of power for a micropulse duration. We then take our measurement and we repeat this process. As we repeat this process, we increase the time pulse, and in order to avoid damaging the FET, we need to apply a buffer or a resistor between the power applied and the device under test. So how can we change resistance? Well, a potentiometer is out of the question because the user would have to manually change resistance, and this defeats the purpose of automation. So then we considered an electronic load or a digital potentiometer, and devices like this aren't suitable for high thermal or high power application and also have very poor timing restrictions. So this led us to our design solution of utilizing a resistor bank, basically a predetermined collection of resistors set up prior to testing. This is where the microcontroller comes in. We utilize other FET devices as switches that the microcontroller could then activate, and that would allow us to select the resistor and also the amount of time that resistor was used for. Another design challenge we had was being able to test two different kinds of FETs. We have smart FETs and we have discrete FETs. The important distinction being these two devices have different measurement circuits required to test for thermal resistance. We approached this problem with a motherboard daughter card strategy. Basically, the motherboard would house the two different measurement circuits, and the daughter card would then later be specifically designed for each device in such a fashion that when you insert it into the motherboard, it will utilize the measurement circuit necessary for that particular device. Currently, we have finalized schematics and are working on the PCB layout to be sent out for manufacturing.
One of our key accomplishments for the software side is communicating with the bench equipment. This is important because in order to fully automate the system, we need to be able to send commands and acquire data from various equipments, such as the power supply, multimeter, and oscilloscope. The most important piece of equipment being the oscilloscope, because these are we going to take the direct measurement of the data. And we were also able to store sample data into an Excel file for future analysis. For our remaining challenges, the PCB board has to be manufactured and tested so that we know if we need to make any changes before doing any automated test. Some of the tests that we will be performing are checking for internal failures within the board, as well as the communication between the computer and the board. This project is meant to be able to test multiple devices simply by changing out daughter cards that will be designed on a case-to-case basis. The software interface has to be finalized and make it more user-friendly so that the future users can operate it easily. One of the challenges is also to filter out the data points taken from the oscilloscope to get more accurate results. And we still need to achieve a fully automated test that works with multiple daughter cards, and the man hours is reduced from 2 weeks to 1 day in order to demonstrate having successfully achieved the best anticipated outcome. Lastly, we would like to thank our technical directors, Kevin and Akash, who are sitting in the back, and our capstone director, Dr. Zunak. Thank you.